Okay, so my name is Aki Yamamoto. I'm one of the chairs of this session. It's my great pleasure to introduce Professor Kazumasa Iida of Nagoya University. So I would like to briefly introduce his research history. He received his PhD from Nagoya University in 2003, and he worked as a postdoc researcher at University of Cambridge from 2004 until 2007. And then he moved to IFW Dresden as a senior scientist. And from 2014, he has been an associate professor of Nagoya University. So he's, as you know very well, his research experience covers a wide range of materials involving ferrite magnets and bulk superconductors and cuprate and iron-based superconducting thin films. So today he's gonna give us a talk, and his title will be Iron-based superconducting thin films, so evaluating the application potential. So Professor Iida, please start.
Okay, thank you very much for kind introductions and also the good afternoons and morning and good evening, everybody. So I'd like to thank the organizer for giving me the invitations. And unfortunately, I'm not in Turkey, and I really would like to be there and to present our work. But unfortunately, I'll give a talk online. And the title has already announced by Aki, and this work is mainly supported by the Kakenhi, and also the main big sponsor is a JST Quest, and this project has been led by Professor Aki. Okay, to begin with, I would like to thank my colleagues for contributing to this talk. This neodymium iron arsenic oxide thin films has been prepared by my former student, Mr. Kondo, and currently Mr. Chen and Professor Hatano and Ikuta. And very nice, excellent epitaxial thin films have been of the potassium doped barium 122 thin films have been prepared by the PhD students of Tony Hing. And also he's from the Professor Yamamoto's group of the Tokyo Agriculture and Tokyo University of Agriculture and Technologies. And also the very beautiful microstructure analysis and also the informative result will be given by the Professor Hata's group of the Kyushu University. And high field transport properties have been investigated by Chiara Tarantini from the Upright Superconductivity Center, and also the Jens Hänisch from Karlsruhe Institute of Technologies. Okay, here is an overview of my presentations. First, I briefly talk about the background and motivations, why we are working on the iron-based superconductors, especially in the form of epitaxial thin films. And then I talk about how to improve the critical current properties of these materials. And here I will show you two approaches. One is to improve the depairing current density by an overdoping method. And the second one is to improve the infield GSC by introducing the artificial pinning centers. And third, I briefly talk about the boundary experiments on the iron-based superconductors together with our recent activities of these directions using potassium doped barium 122. And fourth, the iron-based superconducting thin films on the technical substrate, and in which I mainly talk about the performance gap between the films deposited on the single substrate and the technical substrate. At the end, I summarize my talk. Okay, as already heard by the previous plenary talk the day before yesterday, we are facing the helium crisis. And here is the consumptions of the liquid helium in Japan in 2018. And as you can see, that nearly 90% of the liquid helium is consumed by the MRI scanner and also the cryogenics engineering. And here is the helium productions in the worldwide, and 85% of the helium production is coming from the United States and Qatar. This helium crisis is mainly by the two reasons. One is that the United States stopped the helium delivery to the private sector, to the US VRM, which is 30% of the world production share. And one reason is that the Qatar 3 project is supposed to start operation in 2019, but delayed. These two main reasons we are facing the imminent crisis of the helium shortage. So I think in the near future, we will really have serious problems of the helium shortage. So in the future, we cannot use a high field magnet because these magnets are cooled by liquid helium. I think the high temperature superconductors having a higher upper critical fields are key to these solutions. So the high temperature superconductors, mainly the cuprates, are the solutions of the problems, but as you know, that the high temperature superconductor, this oxide materials has a serious problems, so-called weakling behavior. So this is a nice EBSD mapping of the sintered YBCO materials. And we know that the inside grain shows very nice properties, but unfortunately, the supercurrent does not flow across large angle grain boundaries. So that is the reasons the superconducting properties of the whole sintered materials shows very small critical current density of 100 ampere per centimeters. So, but once you eliminate the high angle grain boundaries, like in the single crystals or epitaxial thin films, the critical current density is improved significantly at 10 to the power of 4 and 10 to the power of 6 ampere per square centimeters. On the other hand, for the iron-based superconductors, for example, this is a potassium doped barium 1 to 2, which is most important materials for the applications. And these materials in the form of the polycrystalline shows a JC of 10 to the power of 5 ampere per square centimeters. Although this material also has the weakling behavior, but the critical current density is quite high compared to the cuprate superconductors. So basically, these materials, this grain boundary does not block supercurrent flow compared to the cuprate. So this is one of the reasons why we are interested in this iron-based superconductors. In addition to the good grain boundary properties, the iron-based superconductors shows a very high upper critical field. Here is the iron selenium telluride 1,1, and this is one cobalt doped value 1 to 2, and also the 11 systems. And you see that the upper critical field at low temperature exceed 50 Tesla for 1,1 and also the 1 to 2. And for the case of the 11 systems, the upper critical field exceed over 100 Tesla, which is quite large. Additionally, these materials shows very low electromagnetic anisotropy between 1 and 2 at low temperatures. The 1111 system shows a slightly larger between 3 and 5, but compared to the bismuth-based cuprate superconductors, this anisotropy is much small and comparable to the YBCO samples. So these properties are very good for the applications. So now we are interested in the thin films. Why? Because there are several merits. One is that the heterostructures and the phases not yet available as single crystal can be fabricated. And this is a good example of the superlattice of the barium 1 to 2 and the strontium titanate. And these structures are not possible in the natural. And also, it is possible to investigate the strain effect and also play the dimensionality quite easy. So this is the iron selen monolayer grown on the niobium doped strontium titanate, and the TC exceed nearly 100 Kelvin. And most importantly, and it's possible to evaluate application potential by conducting the 3 kinds of experiment. So in this talk, I will briefly talk about each topics in the following presentations. Okay, so the first one is to improve the critical current density by improving the dependent current density by an overdoping method. So quite recently, Stangles reported a very high critical current density of the YBCO films in the overdoped samples. Here is the GC at 5 Kelvin is 90 megaampere per square centimeter, which is almost 3 times higher than the optimally doped YBCO films. So what we can see here is that the penetration depth is decreased by 60% by the overdoping. As a result, the depending current density is almost 1 times higher compared to the optimal doped samples. So this is a simple equations of the depending current density. You can see that the depending current density is proportional to the inverse square of the penetration depth and times inverse penetration. And this is also the proportional to the superfluid density and critical temperatures. So here is the penetration depth and the coherence length of the YBCO as a function of the whole doping concentrations. As you can see that with increasing the whole concentrations, the penetration depth and inverse of the penetration depth is increased, and also the coherence is decreasing. So that is the reasons the overdoping method is in the depending current density, and which lead to the improved self-field critical current density of these materials. So with this in mind, we employ this method to the iron-based superconductors. The 1111 system is our choice of materials because the overdoping is realized by hydrogen doping without compromising the superconducting transition temperatures. And here's the fluorine doping. The substitution limit is only 17%. But if you change to the substitution element from fluorine to hydrogen, you can reach the overdoped regimes up to nearly 40%. Here is a literature survey of the penetration depth as a function of the fluorine concentrations for the various lanthanum 1111 systems. As you see that the penetration depth decrease with increase in the fluorine concentration, but for the coherence length is in the range of 1.4 to 2.7 nanometers. So that means we cannot see the correlations between the fluorine concentrations and the coherence lengths. for the evaluating the crystalline densities, we need a large size of the single crystals or the thin films. But unfortunately, the hydrogen doped 1111 single crystal, the size of the crystal is only a few hundreds microns. So for this case, it is really difficult to measure the critical current density. And I mean, it's very complicated to measure. Under such circumstances, the hydrogen-doped epitaxial thin films have been prepared by the Professor Hosono's and Hiramatsu's group. They employ so-called topotactic chemical reactions. This is really easy to incorporate hydrogen into this. First, the parent compound together with the calcium hydride powders are sealed in the quartz tube and annealed at relatively low temperatures. And you obtain the hydrogen-doped epitaxial thin films. And this method is very, very simple, but a very effective way for the hydrogen doping once you prepare the parent lanthanum iron arsenic oxide films. And we employ this method to incorporate hydrogen into the films. And first, we prepare the parent compound of the neodymium iron arsenic oxide. And here is a very nice C-axis textures of the films obtained. And the film thickness was evaluated by the X-ray reflectivity, which shows around 24 nanometers. And for the comparative studies, we also prepare the fluorine-doped 1111 thin films. But unfortunately, this fluorine doping is also some problems. So that is the reason we employed so-called two-step process. First, we prepare the parent compound, and then we deposit a neodymium oxyfluoride overlayer. And during the depositions, the fluorine diffuse into the parent compound, become fluorine-doped superconducting 1111 films. For the hydrogen-doped 1111 films, we sealed the parent compound together with the calcium fluoride hydride powder and annealed at 400 degrees to 500 degrees up to 72 hours. And this is summarized of the resistivity curves of the parent neodymium 1111 films, as well as the fluorine and hydrogen-doped 1111 films. And as I mentioned before, the hydrogen doping case is we obtained the overdoping state. That is the reason the resistivity in the normal state is the smallest for this hydrogen-doped sample. So for both hydrogen and fluorine-doped sample shows a TC around 50 Kelvin. Okay, now we plot the superconducting transition temperatures as a function of the C-axis length, because the C-axis length correlates with the carrier density as shown on the right-hand side of the pictures. So these solid symbols represent the onset TC, and open symbols represent the zero resistance temperatures. And when we dope the fluorine, only a small amount of fluorine induce the superconductivity with a TC around 50 Kelvin. And in the same time, the C-axis lattice parameters is decreased. But up to the C-axis length reaches 8.54 angstrom. At the same time, we measure the carrier density by the Hall method. And the carrier density was estimated at 50 Kelvin by a single carrier model. And as you see that the maximum carrier density reaches 2 times 10 to the power of 21 cubic centimeters. And in this graph, we plot our hydrogen-doped sample. You can see that the C-axis lattice parameters varies quite wide range up to 8.44 angstrom. At the same time, we measure the carrier density of these materials, and the maximum carrier density reaches 6 times 10 to the power of 21 per cubic centimeter, which is almost 3 times higher than fluoride-doped sample. Now we measure the critical current density using this film. And here is a field dependence.
Ой, кошмар. То есть, да. Ну, я могу себе представить, просто его обманули. То есть водили за нос, с морковкой поманили. Да, вот. То есть, если бы, значит, не это, он бы еще, может, жил. То есть, если бы...
Excuse me, could you mute? Okay. Okay, so this is a field dependence of the critical current density of the hydrogen-doped samples and our best performed fluorine-doped samples measured at 4.2 Kelvin. And very surprisingly, we obtained very high critical current density over 17 mega-ampere per square centimeter, which is almost comparable to the heavy ion irradiated barium-1111 single crystal. And this value is almost 30% of the dependent current density of the fluorine-doped 1111 films. And the right-hand side is the pinning force density as a function of the applied magnetic field. And our pinning force density of the hydrogen-doped samples is almost 1.5 times higher than the fluorine-doped 1111 films. And we also evaluate the upper critical field and the irreversibility field for the field parallel to the C directions. And this red ball represent the hydrogen-doped samples, and the blue symbols are fluorine-doped samples, and the open symbols are irreversibility field, and the solid symbols is the upper critical field. And to make a comparisons, we replot the data as a function of the reduced temperature. You see that the HC2 for both fluorine and hydrogen doped samples are comparable, but the irreversibility field is higher than that of the fluorine doped samples. So this is because of the increase in the interlayer coupling, which is similarly observed in the cuprate with the overdoping samples. Okay, next one is to improve the infield critical current density by introducing the artificial pinning centers. And this strategy has already been established in the cuprate, especially YBCO samples, for example, the multi-layers and quasi-multi-layer approach, and doped or perovskite type materials into the PLD target, and also the irradiation method. And in the general result shows that the iron-based superconductors are quite robust against the irradiations or disorder. For example, here the TC is not decreased, rather increased for the irradiations, and also the alpha particle irradiations, the TC decrease quite small, only 3 Kelvin, even you irradiate 5 times 10 to the power of 15 per square meter. But for the doped case, in this case, the value 1 to 2, but nevertheless, the TC decreases almost 1 Kelvin per mole percent, which is quite large compared to the cuprate superconductors. And for the next slide, I will show you some examples. Here, the quasi-multi-layer approach and the barium zirconate addition to the PLD target and the proton irradiations. Okay, the first one is a quasi-multi-layer approach. And Searle et al. Make a quasi-multi-layer using the iron selenium telluride and the selenium oxide. And they deposit only 2 pulses in between the selenium oxide. And here is a cross-sectional TM image of this such a quasi-multi-layers and corresponding strain mapping of these materials. And as you can see that the close to the this strain selenium oxide layer is present, we observe the strain here and here. Because of this strain, in-field critical current density, as well as the angular dependence of the GSC, is improved significantly. For here, 10 Kelvin, you improved nearly 350%. And the second one is the target modifications. This is the barium zirconate added to the cobalt doped barium wanted target. And when doped to 2 more % of the barium zirconate, the in-field GSC is really improved compared to the preceding samples. And this improvement is increased with increasing the applied field. At 14 Tesla, the GSC is improved by 1,400%. And finally, this proton irradiations into the iron selen telluride films, and they observed the cascade sprayed structure in the materials, and the TC is improved by 0.5 Kelvin, and the in-field GSC is improved by 50%. And I show you the several examples is only iron selen telluride and cobalt doped barium 122. But as I mentioned before, the potassium 122 is the most important material for the applications. So we should somehow improve the critical current density of these materials, because this materials is so attractive because the TC is quite close to the MgV2, and the depending current density is the highest among the iron-based superconductors, and also it's low electromagnetic anisotropy. So now, because of the good materials, many people are trying to make bulk magnet as well as powder into processed wires as a proof of principle studies for the applications. Now all material forms except for the epitaxial thin films available in this potassium doped strontium or barium 122 systems, which is a sharp contrast to the other iron-based superconductors. But quite recently, we have successfully fabricated potassium doped barium 122 epitaxial thin films on the calcium fluoride substrate. And here is a summarize of the structure characterizations by X-ray diffractions. And you see that there's a grown epitaxially, and this is a cross-sectional view of potassium doped barium 122 films grown on the calcium fluoride substrate. The key to success is to employ the fluorine substrate as well as the low growth temperatures. And here you can see that columnar grain grew almost perpendicular to the substrate, and each grain rotate around the A-axis or B-axis as well as C-axis. So that is the lot of grain boundaries and networks created inside materials, and these defects work as very strong pinning centers. And here is the pinning force density of our potassium doped barium 122 thin films. As you can see that the pinning force density is almost 10 times higher than the pristine single crystals and comparable to the heavy ion irradiated samples. So now I talk about the grain boundary experiment on the iron superconductors. So far, the 1111, 122, and iron selen tellurides, the grain boundary experiments have been conducted. The common features of the result are the critical angle for which the intergrain GSC decrease exponentially is around 9 degrees for all systems. And also the constant intergrain GSC over 24 degrees was observed for the cobalt doped 122 as the iron selen telluride. But so far, no investigations of the potassium doped 122. Again, I mentioned that this material is the most important materials in the iron-based superconductors in terms of the applications. But as mentioned before, that we have successfully fabricated epitaxial thin films on the calcium fluoride. But unfortunately, as far as I know, that the bicrystal calcium fluoride substrates are not commercially available. Only the oxide bicrystal substrate, such as magnesium oxide, strontium titanate, sapphires, and ersatz available. But the barium 122 and cobalt doped barium 122 grow epitaxially on those substrates, so which is good. But for the strontium titanate, the oxygen is usually reduced during the depositions, especially in the ultra high vacuum conditions. For the ersatz substrate, reaction layers is always present at the interface between the barium 122 and the substrate. But as mentioned before, the barium 122 parent compound can be grown on the magnesium oxide substrate. So that is the reason we consider that this barium 122 as a potential buffer layer to grow potassium doped barium 122 by the several reasons. One is that the lattice mismatch between the parent compound and potassium doped 122 is small. And secondly, the potassium doped barium 122 is chemically inert against the barium 122. And here is our architectures of the potassium doped barium 122 grown on the barium 122 buffer layers. So first, prepare the buffer layers having approximately 20 nanometers at 720 degrees, and followed by potassium doped barium 122 having 80 nanometers deposit at 400 degrees C. Because this potassium doped barium 122 is sensitive against the moisture and water, we deposit the cover layers of the calcium fluoride on top of it about 30 nanometers. So here is a cross-section view of the TM image of this bilayer structures. And as expected, we obtained very nice sharp interface between the barium 122 buffer layer and the potassium doped barium 122. And here is the structure characterizations of potassium doped barium 122 bicrystals having grain boundary angles is 13 degrees. And you see that very nice C-axis textures are observed. But by looking at 404 and 08 reflections, two peaks arising from the potassium doped barium 122 and the parent barium 122 buffer layers are observed, which means that the potassium does not diffuse into the parent compound. And here is 1035 scans that two domains separated by 13 degrees of the grain boundaries angles observed. That means we have successfully paired the potassium doped barium 122 bicrystals in the barium 122 buffer layers. And here is superconducting properties using the intragrain and intergrain, having different grain boundary angles from 6 degrees to 30. And we also provide magnetic field parallel to the crystallographic C-axis from 0 Tesla to 9 Tesla. And for the grain boundary angles of the 6 degree, you see that the TC is almost same as intragrain and intergrain. That means the potassium is homogeneously distributed within the films. And also, when we apply the magnetic field, shift of the TC is quite small, and even which is almost same as intragrain as well as intergrain. And the other grain boundary angles also same as the 6 degree, but the TC is quite slightly lower compared to this one because we intentionally make the films with overdoping for these 3 angles. Okay, here is the field dependence of the critical current density of the intragrain and the intergrain grain boundary angles of the 6 degree. And we measured from 12 Kelvin to 30 Kelvin. And below 12 Kelvin, unfortunately, we cannot measure because of the heating problems. And you see that the self-field GSC of the intragrain GSC is almost ampere per square centimeter at 12 Kelvin, which is almost same as the intergrain GSC. And for the intergrain bridge, we applied a magnetic field, but the GSC does not decrease significantly, and which is almost same as the intragrain behavior. And here again, I show you the absolute value of the intragrain GSC and the intergrain GSC. Both are almost 1 mega order of the ampere per square centimeter, which is 1 order of the magnitude higher than the bulk single crystals, as well as the polycrystalline samples. So here is the same plot, but we plot together the intragrain and the intergrain GSC as a function of the applied magnetic field. As I mentioned before, the grain boundary angles of the 6 degree is almost the same GSC for the intra and the intergrain. And we plot also the 13 degree and 24 degree of the samples, but unfortunately, we observed the weakling behavior of the 13 degree and the 24 degree. As you can see that even the small magnetic field GSC is dropped significantly. But nevertheless, the GSC is quite high and maintained over 1 mega ampere per centimeters. So now we plot the intergrain GSC as a function of the misorientation angles for the comparisons of the cobalt doped barium 122 measured at 12 Kelvin and the iron selenide telluride measured at 4 Kelvin are also plotted in the same figure. And here is our data of the 12 Kelvin. As I mentioned before, the intergrain GSCs exceed 1 mega ampere per square centimeter, which is quite high compared to the cobalt doped barium 122 and as iron selenide telluride. Of course, this is not a fair comparison because the TC is high, and therefore we measure the intergrain GSC at 12 Kelvin, which is 20 Kelvin, which is half of the TC. But even half of the TC, the intergrain GSC is much higher than the cobalt barium 122 and also the iron selenide telluride, which means that the GSC at a higher angle seems to exceed to the other iron-based superconductors. And we plot the normalized GSC as a function of the misorientation angles. But in this case, the trend is almost same as the other iron-based superconductors. But here, still, the grain boundary angles of 24 degrees is higher than the other iron-based superconductors. Okay, now I'll switch to the thin films grown on the technical substrate. I almost consumed the time. And here is a summarize of the iron selenide and the barium 122 films grown on the technical substrate, as well as the single crystalline substrate. And here for the 1-1 systems, Rabbit's templates and also the IVAT templates both have been used. But here, especially in this case, the 1-1 grown on the Cerium O2 buffer, the Rabbit templates shows almost same as the property of the grown on the single crystalline substrate. That means the performance gap is almost negligible between the films grown on the substrate and the single crystal substrate. But for the barium 122, we clearly see the performance gap here for the phosphorus of the barium 122 and the cobalt doped barium 122 as well. And we fabricated 1111 films on the IVAT template. And in 2014, we reported the GSC of the below 10 to the power of 5 ampere per square centimeter. But 7 years later, we improved significantly of the critical current properties of these films grown on the IBAT MGO, although the still performance gap is still there. And we check the microstructures of these materials, and we see a lot of defect inside the films. And here is a schematic illustrations of defect present in our films. But nevertheless, these defects work as a very strong pinning center, especially in the magnetic field. Okay, let me summarize my talk. The overdoping method reported in the cuprate is applicable to the lanthanum iron arsenic oxide by hydrogen doping. Low-angle grain boundary networks in the potassium doped barium 1 to 2 work as a very strong pinning center. The critical angle of the O1 tilt grain boundaries for the iron-based superconductor is around 9 degrees. Potassium doped barium 1 to 2 shows a high intergrain JC compared with the other iron-based superconductor. The performance gap between the films on the single crystals and the technical substrate are present for the 1 to 2 and the 1111 systems, and such gap is almost negligible for the 1-1. And for the perspective, the iron-based superconductors may win against the cuprate in terms of the cost. That is the reasons, and Professor Ma's group in China push to the iron-based superconductor to become real applications. With this, thank you very much for your kind attention.
Thank you very much, Professor Iida, for very nice, comprehensive talk from basic to applications, and also on variety of materials. So now this session is open for questions and discussion. Is there questions from the room or audience from online?
Yes, hello. Yes,
Please.
Germán de la Fuente from here in the room. It's nice to say hello to you. And I look forward to see you all next time here. Yes, I was thinking about the comparison in JC.
Yeah.
At 4.2 Kelvin that you showed at the beginning between this type of superconductors and YBCO, for example. Do you have any idea what the comparison is like, let's say at 20 Kelvin, for example? At the same temperatures, yes. Because the JC for YBCO was at 77 Kelvin.
Yeah.
And the one for the iron superconductor was at 4.2 Kelvin. So is there a comparison at the same temperature?
Okay, for example, say 20 Kelvin. Okay. For the zinc, yes, for example, this one, even 20 Kelvin, the T is over 1 mega ampere per square centimeter. So that means the single crystal or even the sample containing grain boundaries is quite large. But of course, this is not a fair comparison. For example, this one, the grain boundary angles of 24 degrees, 20 Kelvin, but still GSC is over 10 to the power of 5 ampere per square centimeter, which is quite almost comparable.
But the interesting thing would be to compare it with YBCO at the same temperature.
Yes.
Both at 20 Kelvin, for example.
Yeah, or for example, it's better to compare to the same reduced temperature. Yeah.
But a very nice work. Excellent lecture.
Yeah.
Thank you very much.
Thank you for pointing important point. Is there other questions? from the room? Okay, please.
Any questions from Zoom room, let's say?
Okay, actually, I have one question. So if we look at this slide, it is quite interesting to see that grain boundaries JC, intergranular JC is sometimes higher than grain JC. Do you have some idea about this?
Yes, I think it's some kind of grain boundary pinning, especially for low, especially for the low field, and this is also sometimes observed in the films grown on the technical substrate.
Is it also observed in YBCO?
Yes.
Okay, thank you. Is there other questions? Okay, so if not, time is a little bit passing. So let's thank our plenary speaker again.
Thank you very much.